All right, everyone. Welcome back to another Math 141 lecture series where we are going to continue talking about the mathematical theory of elections. Previously, we've talked about 4 different voting methods: plurality, Borda count, pairwise comparisons, and plurality with eliminations, also known as instant runoff voting. And many times in previous videos and in class, I have asked which election method was the fairest. I've been asking you to kind of give an opinion about fairness of these elections. But the purpose of this video is to try to attempt in a somewhat mathematical way to quantify fairness for elections. What we're going to do is we're going to give 4 criterion, which we can mathematically check. And each of these criterion in some way is going to tell us some notion of fairness that an election ought to satisfy. So let's dig into it. The first fairness criterion that I would like to talk about is something called the majority criterion. So this basic idea of the majority criterion is as follows. In an election, no matter how we count the votes, if a candidate receives a majority of first place votes, then they should be the winner. So why does this quantify fairness? If a majority of voters prefer one candidate the most, it seems fair that that candidate should win. And many methods of election satisfy the majority criterion, right? If we have a plurality method election, if you win a majority, then you are declared the winner. So with respect to the majority criterion, the plurality method of election is fair. And I emphasize the quote unquote right there, right? We're just adding some criterion, sort of axioms for fairness. Whether these are actually fair might more be the topic of a philosophy course or something of that nature. All right, so this is the idea. If a candidate receives a majority of first place votes, they should be the winner. And here what I'd like to do is consider the following example. So right here, I have a preference schedule for an election with 3 candidates. I have J, H, and G. And what we'll do is calculate the winner of the election using the Borda count method. I want to ask, is the majority criterion satisfied in this particular election? So we've already done some calculations of the Borda count. So if you want to pause and try to calculate and compare your results to mine, that's fantastic. But I'm just going to move on and unveil the results for this particular election right here. The first thing that we do in any election like this is calculate the place table. So when we're doing the Borda count, it's the easiest to have the place table in order to calculate this. So this table summarizes all the first, second, and third place votes achieved by G, H, and J. And then what we can do is we can just calculate the points that each candidate gets under the Borda count. There's 3 candidates in this election. So that means that we multiply the first place votes by 3, the second place votes by 2, and the third place votes by 1 for each individual candidate. That determines their points. And then the Borda count election winner is decided by who has the most points. And so right here, I showed my work. You can pause to check it, but the points for G is equal to 32. The points for candidate H is 46, and the points for candidate J is 42. So that means the complete ranking is H, J, G, and candidate H is the winner. One thing that you might notice is that in this election, we have 20 total voters. So that means a majority is 11, right? 20 divided by 2 is 10, but 20 is even, so we have to add 1 to have a majority. And if we look right here at this column in the preference schedule, candidate J does have a majority. But under the Borda count method, they are not declared the winners of the election. Therefore, the Borda count method can violate the majority criterion of fairness. So in the sense of if we consider the majority criterion fair, the Borda count method is somewhat unfair because it doesn't satisfy the majority criterion. All right, well, that's maybe a somewhat disconcerting example, but let's study other notions of fairness that could possibly show up. So we'll need a definition. So in an election, the Condorcet candidate, now I surely pronounced that wrong. I don't speak French or whatever word that is, but I'll just call it the Condorcet candidate. The Condorcet candidate is the candidate preferred by a majority of voters over every other candidate when compared in head-to-head comparison. So in view of the method of pairwise comparisons, the Condorcet candidate would win in every single pairwise comparison. They would achieve a perfect score in the method of pairwise comparisons. So that's what a Condorcet candidate is. It's one preferred by a majority of voters to every other candidate. A standard disclaimer not every election has a Condorcet candidate, but some might. Condorcet candidates sort of motivate the second notion of fairness right here. And that's the following. If an election has a Condorcet candidate, then that candidate should be a winner. So if we prefer one candidate to everyone else, right, when we look pairwise, that candidate is probably most preferred overall and should be declared the winner. Indeed, in this setting of fairness, the method of pairwise comparisons is fair because the Condorcet candidate gets a perfect score. However, and I think you might start getting the hint of how this lecture is going, not every election is going to satisfy the Condorcet criterion. So right here, I have the preference schedule for an election between 5 candidates, A, B, C, D, and E. So first, we'd like to find the winner of the election using the plurality method. And then I want to ask a separate question. Is there a Condorcet candidate, and is the Condorcet candidate the winner? So why don't you pause the video and try to figure these things out, and then unpause when you're ready to see the solution. All right, now that everyone has unpaused, we can sort of unveil our solution right here, which works in multiple parts. So the first question was find the winner using the plurality method. Now, candidate A has the most first place votes. They have 37, B has 36, and candidate C has 4 first place votes. So A wins under the plurality method. And the next question I ask, is there a Condorcet candidate? And it might be a lot to test, but one thing that you might notice from this election right here is that candidate B is pretty popular, right? Overall, right? First and second place in a lot of different, for each of the preference schedules. So maybe candidate B is a natural candidate that we can check if they're a Condorcet candidate. Indeed, if we look at the head-to-head between B versus A, well, B gets 40 votes and A gets 37, right? These 37 prefer A, but these 36 plus 4 prefer B to candidate A. So B is preferred over A, and then B is super popular. All candidates prefer B over D, all candidates prefer B over E, and most candidates prefer B over C. So C is preferred over all other pairs of candidates. This means that B is a Condorcet candidate. However, they do not win under the plurality method. So what does this mean? This means, in particular, that the plurality method does not satisfy the Condorcet criterion. So I'll just write that down here. Therefore, the plurality method does not satisfy the Condorcet criterion. So in the sense of the Condorcet criterion, the plurality method is, again, unfair according to this one axiom. All right. So let's scroll down to our third fairness criterion called the monotonicity criterion right here. And here's what the monotonicity criterion says. If candidate X is the winner of an election, then X would still be the winner had a voter changed their mind and ranked X higher in their preference ballot. Another way of saying this is that a candidate should not be penalized for having retroactively a candidate rank them higher up. Like ranking a candidate higher up should only benefit that candidate when compared to the previous situation. To me, the monotonicity criterion seems obviously like a very fair thing. It would be very paradoxical to me if by ranking a candidate up, I actually hurt their chances of winning the election. All right, so what I'd like to do is study 2 different examples. So in this first example right here, we have an election between 3 candidates with the following preference schedule. And what I'd like you to do is figure out the winner of this election using plurality with elimination. Again, you can pause and figure this out. I'll unveil the answer. All right, so let's unveil the answer right here. So with plurality with elimination, what first we want to do is find what is the majority in this election. So there are 27 voters and the majority threshold is 14 total. So we'll notice that candidate A has 9 total first place votes, B has 8, and C has 10. So this means that we are going to eliminate B, who has the fewest amount of first place votes. None of the candidates achieved a majority, so we have to eliminate the last one and then recalculate the preference schedule and retabulate the first place votes. That's how the plurality with elimination method works. So if we do that, we arrive at the following new preference schedule right here. And what do we notice if you unveil everything is that after eliminating B, we count that C has 18 first place votes and A has 9. Since C has a majority, C is the winner. So in this election, under plurality with elimination, C is the winner. Let's move on to a new example. So what we're going to do in this example is suppose at the last minute before ballots were due, the two voters in the last column of the preference table above, so these two voters right here who preferred A to C to B, what they did is they changed their minds and they switched at the last minute from candidate A to candidate C. So that would result in the following preference schedule. These three columns are going to stay the same. I haven't changed them from before. But what happens right here is these two voters have swapped A and C. So these two voters have ranked C higher up in their ballot. So what I'd like you to do is pause and figure out who wins the selection using the plurality with elimination method. All right, so after now that you've unpaused, I am going to reveal the results of what happens about who wins the selection using the plurality with elimination method. So again, there are 27 voters in this election. I didn't change much about it. I only changed this last column, and that's going to give a majority threshold of 14. Now what's happened is that A has 9 first place votes, B has 8, and C has 11. Actually, no, I need to fix that quickly. Ooh, good thing I caught that. So let me fix that right there. So A has 7 first place votes, right? They only received the first place votes from this particular column right here. B has 8 first place votes, and now C has 11 first place votes. So no candidate has a majority, so we need to eliminate the person with the candidate with the fewest amount of first place votes, so we eliminate A. After we eliminate A, their first place vote is transferred to candidate B instead. So if we look at the new preference schedule for the election, and we calculate who is the winner, just using the plurality method after this first round of elimination, we'll see that B now has 15 votes, and that is a majority. So in this case, B wins the election. So this means plurality with elimination violates the monotonicity criterion. In the first election, candidate C was the winner. The second election is the same as the first, except the last two ballots in the preference schedule changed their minds and voted C ahead of A. So C gained more first place votes. Despite that, they now lose in the resulting election using plurality with elimination. So the monotonicity criterion has been violated. So in plurality with elimination, what can happen is that by changing your mind and ranking a candidate higher, that can actually make them somehow lose the election. So that contradicts the following fairness criterion. So plurality with elimination. So if a candidate X is the winner, then X would still have been the winner had a voter ranked X higher in the preference ballot. That's violated in that case. So with respect to this fairness criterion, plurality with elimination is a little bit unfair. Let's continue on to our last fairness criterion, and this is called the independence of irrelevant alternatives criterion, also known as the IIA criterion. And what this criterion says is the following. If candidate X is the winner of an election, then that candidate would still be the winner had one or more of the irrelevant alternatives, in other words, losing candidates, not been in the race. So we can study this fairness criterion using the method of pairwise elimination. So right here, I have the following preference schedule for an election with 5 candidates. And there's a lot going on here, but we're not actually going to calculate with it. It takes a while to check, but candidate A is the winner of this election by using the method of pairwise comparisons. If you check all 10 pairs, A ends up with the most points using that rule. All right, so A is the winner. So to test if this election satisfies the IIA criterion, what we can do is just see what happens if we dropped an irrelevant alternative from the candidate. What happens if we drop candidate C? In that case, this is what the preference schedule becomes, right? I took C out and I moved everyone up a stage that had to be moved up. So if C was 3rd place in a preference ballot, the 4th and 5th place are moved up 1 spot. So after removing C, this is the resulting preference schedule. And it's a fact that you can check, maybe you can pause the video. is that candidate B is the winner of this election using the method of pairwise elimination. So what's our takeaway right here? Our takeaway is that the method of pairwise comparisons violates the IIA criterion. At first, candidate A was the winner, but when an irrelevant alternative, candidate C, was dropped, B became the winner. So what have we shown? We have shown, looking at all of our fairness criterion, that the board account method fails the majority criterion. The plurality method fails the Dorchet criterion. Plurality with elimination fails the monotonicity criterion, and pairwise elimination violates the IIA criterion. So all methods of election that we've studied are unfair with at least one of these criterion. Again, fairness is just determined by what that criterion says. It turns out that there's a very impressive theorem about mathematics, which is a bit of a downer, and that's called Arrow's impossibility criterion. It says the following: consider any election with 3 or more candidates. Then any voting method, including ones described above or those that have not even been invented yet, violates at least one of the fairness criterion. So this is a picture of Ken Arrow right here. What it means is no matter how you set up an election, it will violate one of these 4 fairness criterion. On the one hand, this is a bit of a bummer of a result, but on the other hand, elections are a necessary part of life. By understanding the mechanisms of an election, we can pick the best option for each election's circumstances. And understanding that there's a potential for fairness criterion to be violated helps us have more nuanced discussions surrounding elections, right? No one election is going to be better than the other method of election. We have to compare their merits and how they work against each other. It's why it's very, very, very important that we are educated consumers when it comes to our knowledge of different voting methods. One standard disclaimer: Arrow's theorem asserts that any voting method could have one of the fairness criterion violated. It doesn't mean that every individual election is unfair, but that there are examples of elections using these methods where the fairness criterion are violated. So just one last thought. We've discussed some sort of mathematical ideas for fairness, but the 4 criterion of fairness we discussed are certainly not the only ways that an election could turn out to be unfair. So for example, certain state and local standards result in very confusing ballots. So I found one of these Florida ballots right here, and it turned out what happened with these ballots is it was very confusing about how to select each candidate. So if you're voting for a Republican candidate, you might accidentally vote for a Reform candidate, or you might accidentally vote for a Democrat or a socialist when you might have tried to vote for either one of these. So certain state and local standards can result in just very confusing ballots. So in our course, we have not addressed that type of defect. We've only addressed mathematical ideas. So our mathematical models are not going to be definitive perspective, but I think they're very helpful perspectives that we have as we try to judge the merits of elections. It's just one tool in our toolkit. And then I'd just like to conclude with a real world takeaway. In many states, various referendums have been introduced to allow things like plurality with elimination, instant runoff voting to happen in important elections in the United States. So I hope that your study of the various election methods helps you develop an educated opinion on this important issue. Most of us are likely to vote on such a referendum at some point. So by being more educated, we know that we can confidently make a better decision. All right, thanks.